Welcome to the fourth out of 5 lectures in Unit 6, Earth's Dynamic Atmosphere. This lecture will cover material from Chapter 19, Weather Patterns and Severe Storms. Weather patterns and storms are influenced to a large degree by the air masses from which they originate. Air masses are large bodies of air. Remember, we can think of aspects of the Earth system often in terms of their systems and their subcomponents or subsystems. Air masses are consistent with this idea, and they are basically large bodies of air that behave in similar or in a consistent fashion. Now, air masses are not discrete entities entirely, that is, they transition into other air masses, and so to define an air mass as it is shown in this picture to the right isn't that exact or isn't exactly correct insofar as an air mass doesn't have a sharply defined boundary as shown there. Air masses are generally about 1,000 miles or more across, can be several kilometers thick. They are defined by temperature and moisture, that is, similarities in temperature at any given altitude and similarities in moisture content or relative humidity at any given zone in that air mass. And they are mobile, they move, and they are able to affect large portions of continents or spatial areas of the globe. Now, air masses generally have a source region, that is, an area where an air mass comes to be or arises tends to influence its properties. So air masses will take on the properties from the area from which they're formed. Air masses can be classified several different ways based on their source region. Air masses are classified based on their source region in two different aspects of their source region. That is the latitude as well as the nature of the source region. So latitude is generally is divided into two zones, tropical and polar. And the nature of the region in which an air mass arrives can be either continental or maritime. So with these two latitude zones and two nature of the surface regions, you can arise or you can create 4 different types of air mass. The two latitudinal zones of air mass formation are polar and tropical, and polar tends to be high latitude cold, tropical is low latitude and warm, which makes a lot of sense, and then the continental and maritime are relatively self-explanatory as well. So there are 4 basic types of air masses, not air mattresses. There's only one type of air mattress, I guess. That's the kind that's uncomfortable. 4 basic types of air masses: continental polar, continental tropical. Both are relatively dry, and the difference between a continental polar and a continental tropical are the relative to the air temperature, or is the air temperature of the masses. Maritime air masses, on the other hand, are characterized by humid air. And if they're polar or tropical, again, is defined by temperature. So maritime polar are going to be cool and humid, and maritime tropical are going to be warm and humid. Air masses of the continental polar and marine tropical have the dominant effect in North American weather and climate. That is, continental polar masses from northern Canada and interior Alaska bring generally cold, dry air into the North American interior. In the wintertime, that brings cold, dry air, and in the summertime, that cold or cool air is pretty welcome. In wintertime, not so much. They're also responsible for lake effect snows as cold air masses move across large bodies of water, the Great Lakes in particular, pick up moisture from the lakes, and then due to a supersaturated state of those air masses as they move over, again, cooler landmass causes precipitation to form. Maritime tropical air masses originate in the Gulf of Mexico and the Atlantic Ocean, and they tend to bring moist, unstable air to the eastern zone of the United States. Now, maritime polar air masses in the western United States, and particularly in the Pacific Northwest, and continental tropical air masses in the southwestern United States do influence climate in those regions as well. And polar tropical, maritime polar air masses in the northeast United States, moving from a northeast to southwest direction, can bring nor'easters and lots of winter storm activity. But again, the dominant air masses that influence broad swaths of North American climate are continental polar and maritime tropical. Now, a front is a boundary that separates air masses of different densities. And again, I caution you to think of fronts as being these sharply defined zones of air, although in some cases, the front or the boundary zone can be quite steep or quite sharp. Air masses tend to retain their identities when they interact, and warm, less dense air in either a tropical maritime or continental tropical air mass tend to move aloft or upwards relative to cool, denser air, typically polar fronts. At a warm front, warm air is replacing cooler air. That is, in this graphic, the dominant motion of air masses is moving left to right, or if we were on a map, it would be west to east. Cool air is moving to the right, and warm air is moving to the right. So warm air is replacing cold air. As those air masses move and interact, warm air is moved aloft, moves above, or moves upward relative to the cool air. Again, this is akin to subduction processes in the plate tectonic model, or as water masses move in the global ocean thermohaline circulation. On a weather map, you see this symbol for a warm front, basically the contact zone between a warm air mass and a cool air mass, as a line with semicircles on the front side in the direction of motion. Clouds become lower as the front progresses over an area. Relatively slow rate of advance, and there is light to moderate precipitation in these zones due to the fact that warm air, which has a high capacity for water at the surface, as it raises or goes aloft and cools, the relative humidity increases, and eventually it reaches that condensation point. You can see the different types of clouds that occur, and as we saw before in the cloud, in the lecture the lecture that described the different cloud types, these nimbostratus, remember nimbo meaning rain, stratus, low-hanging sheet-like clouds will produce produce moderate precipitation, and as that air mass rains out and becomes drier, the condensation that still remains and forms creates either altostratus clouds or cirrostratus and cirrus clouds. Cold front, on the other hand, is where cold air is replacing warm air. You can see it's a much steeper front face. It's shown on weather maps as a line with triangles in the direction of motion. It's twice as steep as a warm front. It advances much faster than warm fronts, and the weather is more intense. That's due to the fact that warm air is brought aloft at a much faster rate, which causes condensation to form rapidly, updrafts to bring a lot of warm, moist air high into the zone where it cools, condenses, and precipitation forms. Weather behind the front is dominated by cooler, subsiding air and clearing conditions. But those cumulonimbus, those very, very, very tall clouds that reach from the low cloud zone in 2,000 meters on upwards into 8,000 meters, those form at cold front boundaries. A stationary front is where the flow of air on both sides of the front is almost parallel to the line of the front. That is, air movement is not pushing these fronts across land. In fact, the air movement is right along the front, which causes them to kind of remain still. The surface position of the front does not move in this regard. An occluded front, on the other hand, is where a cold front, which generally moves faster than a warm front, and you can see in image in this triptych to your right, where the low-angle warm front, which warm air is not moving as fast, or the front is not progressing to the right as fast as the cold air front is on the left. this cold air will eventually overtake this front, and we get this light rain on the front, warm air is forced aloft, and really dramatic cumulonimbus thunderstorms are created at the boundary of the warm front and the cold air mass that's overtaking it. Cold air wedges the warm air upward, and the weather is often pretty complex. That is, lots of different types of precipitation and intensities. Moving on to what are called, or to where fronts interact with the global atmospheric circulation of cyclones and anticyclones. In the mid-latitudes, we saw that low and high pressure zones were the dominant atmospheric circulation pattern, and cyclonic activity, that's anticyclones and cyclones. Anticyclones being where there's high pressure zones and divergence, and cyclonic movement where there's convergence and around low pressure centers. These systems dominate in the mid latitudes, and we can see the life cycle of what's called a mid latitude cyclone, how these cyclonic storms form. And as from the 60-degree latitude band of the polar convergence zone, you can see a front developing where warm air and cold air are interacting, a cool air mass trailing a warm air mass moving across the continent. As you start to get a wave, which are due to either surface friction as well as Coriolis forcing, you develop a wave, and what eventually happens is cyclonic circulation, that is, this rotational orientation of the wind bands develop, and you get cold air masses following on warm air masses, which can cause kind of a swirled or really complicated and convoluted overlapping of the warm air and cold air masses into an occluded front, which eventually as it consumes itself, as shown in block E, will consume itself and dissipate. But where air is moving parallel to the front in opposite directions, you can get these cyclones taking place, which generate some fairly intense storm systems over the continental, or over continents in general, North America in particular. The cloud patterns that you typically associate with mid-latitude cyclonic systems are classic occluded front patterns, where the fronts are actually joined and just past where they're occluded, and this transect from G to F. You see that the occluded front has been consumed. There's no longer a warm air mass penetrating to the ground. Warm air is aloft with nimbostratus clouds above, lots of precipitation. In the wintertime, this can yield quite a bit of long-standing snowfall and precipitation. Further to the south, where occlusion is not yet occurring, where you still have a cold front trailing onto a warm air mass that is moving forward on a cold front as well, you get these classic zones of bands of light precipitation ahead of somewhat dry air, and then fairly intense thunderstorm activity in the trailing region. So as a middle latitude or mid-latitude cyclone passes across an area, what you get is this classic warm front weather band of medium intensity showers, relatively slow-moving front, followed by a general clearing period, followed by what is a classic cold front approach, where there's a very steep front, wall of dark clouds, heavy precipitation, and after a cold front passes, then northerly winds prevail, and skies become clear and temperatures fall. The mid-latitude cyclone system produces, basically is influenced by and influences the the jet stream, basically the air, upper level air movement across the continents. The cyclones and anticyclones are generated by upper level air flow. That is, as upper level airflow moves across the continent, variable warming and cooling occurs, divergence and convergence occur as well. These, what are called ridges and troughs, will form in the over continents. As a cyclone advances, it's a low pressure system where you have surface convergence and outflow aloft, basically as air converges at the surface, moves aloft, and then spreads outward at high altitudes. It sustains low pressure and it causes divergence to bring the upper level flow on a northerly bent. Anticyclones, on the other hand, which are zones of surface divergence, air moving downward from high altitude to low altitude, will typically cause a what's called a ridge in the pressure system or the jet stream. Thunderstorm activity is highly correlated with frontal systems and atmospheric circulation. Thunderstorms feature these cumulonimbus, these very, very large clouds, vertically speaking, that can stretch from 1,000 to 2,000 meters high to 6,000 meters high or higher. Heavy rainfall, lightning, and occasionally hail. They occur over wide areas of the continental United States and in the globe. They're typically confined or typically related to areas where maritime tropical circulation patterns or air masses are dominant, or where there's significant geologic vertical structure, that is mountain ranges and orographic lifting. You can see in this pattern, this global map of precipitation patterns, the Gulf Coast, the Gulf region of the United States, this notch in equatorial Africa, and over in the Indian Ocean are zones of very, very intense thunderstorm activity. In the United States, they're most frequent in Florida and Eastern Gulf region, as many of you who are local students know. 2,000 of them are in progress at any given time, and there's over 100,000 per year. Stages of thunderstorm development are fairly standard, fairly well known, fairly well defined. All thunderstorms require a few things. They require warm air, that is air that has a high degree of capacity for water, but it has to be warm because eventually that air has to cool and that moisture has to fall out. But you have to start with moist, warm air. There has to be an unstable air mass. That is, a stable air mass is one that's less prone to changing its location vertically. It has to be an unstable air mass that is subject to lifting or elevation change. High surface temperatures, where you get localized warming and density changes in the air mass, encourage this instability. They're most common in the afternoon and early evening, when solar radiation has had the longest amount of time to interact with the Earth's surface, and generally surface temperatures are warmest. They also require a continuous supply of warm air and moisture to come in from the sides. So they are characterized by lifting, that is, convergence at the surface, and elevation gain of the air mass as it rises. As that warm, moist air mass rises and cools, what happens is the saturation state or the relative humidity increases, condensation forms, and you can get very, very, very dramatic releases, or very intense releases, high magnitude releases of water as precipitation. Tornadoes are a very intense variation on thunderstorm patterns in terms of their generation and location and driving forces. They're usually characterized by very short duration. They're violently, the winds are violent. A rotating column of air extends down from a cumulonimbus cloud, that is the same kind of cloud that is the formation or generates thunderstorm activity. Low pressure inside the cumulonimbus system causes air to rush into the tornado. That is, these are zones of extremely intense convergence. Winds can approach 300 miles per hour. And smaller vortexes within a tornado can produce even more intense environments. So tornadoes occur over a wide area of the United States. There's almost 800 happen per year in the U.S. They're most frequent in the springtime, April through June, and they're associated with thunderstorm activity. Now, the exact cause of formation of tornadoes is not exactly known. However, there's lots of relevant and intense research ongoing on these systems because the economic damage that they produce is so great. So there are plenty of good hypotheses. And in general, what scientists think is the basic or the basis for tornado formation is that strong winds aloft tend to move across a landscape much faster than surface winds due to surface friction. And what you get is this kind of spiraling environment or spiraling wind pattern on the over large vertical swaths of air. When you get localized heating or cool fronts moving through, and you get vertical displacement of warm, moist air, these kind of overturning, rolling bands of air can get kind of perturbed upwards through updrafts and the natural processes that cause thunderstorm formations or thunderstorms to form. If the updraft is intense enough, this band of spiraling, spinning air can get shifted from being a horizontal band to a vertical band, where the spiraling air kind of orients vertically, and you get the generation of the characteristic airflow inflow pattern that is intense convergence that characterizes a hurricane. Hurricanes you get the intense inward convergence of air movement that characterizes tornadoes. Characteristics of tornadoes are that they're roughly 150 to 600 meters in diameter. They can move 30 miles per hour, which is really fast for a storm system, and they can last. They can travel upwards of 6 miles. In fact, there's some recent tornado systems in the last year or two that have traveled much longer than that. These are really intense, damaging systems that are relatively poorly understood. Intensity is measured by the Fujita intensity scale, which will rate tornadoes on a scale of intensity and wind speed. They're difficult to forecast because they're relatively small, and so prediction is difficult. It's hard to have the measurement resolution to understand their formation exactly in such a way that prediction becomes possible. Scientists do know the basic conditions with which tornadoes are likely to form in, but actually predicting when one will pop up and what its path will be is notoriously difficult. So tornado watches are used to alert the public to the possibility that tornadoes might exist. Are issued when conditions are favorable, and they cover large areas, 25,000 square miles, which is a block of land 50 miles by 50 miles. That gives a sense of how hard it is to really kind of know the exact microclimatological conditions that seed or generate these systems. A tornado warning, on the other hand, is issued when a tornado is visibly sighted or indicated by weather radar. And Doppler radar, which is fairly ubiquitous nowadays, helps increase the accuracy by detecting. It can detect the rate of motion of air. Not only does it detect reflectivity or precipitation, it actually gives a vector quantity to air movement. Now, hurricanes are cyclonic systems that are much larger than tornadoes. To be called a hurricane, wind speeds need to exceed 74 miles an hour. Below that, it's a tropical storm, and they are counterclockwise rotation, which by definition is cyclonic. They tend to form in the subtropical band between 5 degrees and 20 degrees latitude in the eastern Pacific and the eastern Atlantic. They move in a general westward direction. They curve due to Coriolis forcing. They're known as typhoons in the western Pacific and cyclones in the Indian Ocean, but hurricanes, cyclones, typhoons are the same thing. The North Pacific has the greatest number of them per year, even though in Florida it would seem like the Atlantic does, because that's what we worry about most here. The physical parts of a hurricane are known to a lot of people, especially in Florida. The eye is the center. It can vary between 10 to 20 kilometers in diameter. Some really, really large systems have very big eyes. There is no precipitation. Wind is generally slackened there, and air is descending through the eye, and that actually it's kind of a backfilling of air as it moves up and moves outward in the outflow band. It's the warmest part of the storm as well. The eye wall, in contrast, is the area of greatest wind speed, has intense convection. That means you're going to have a lot of upward moving air there. It's heaviest rainfall. It's where the most air is moving up with the most water, and as that air moves up and cools, condensation occurs, and that rain occurs as a consequence of that. Hurricanes form in all tropical waters except the South Atlantic and eastern South Pacific due to and those are due to kind of gyre patterns. That is, in the South Atlantic and the eastern South Pacific, you have actually warm water on these western boundary currents flowing through. You need actually you have cold water in the western boundary currents of the South Atlantic and eastern South Pacific that tend to reduce or make hurricane formation unfavorable. In the eastern Pacific and eastern North Atlantic, you have enough solar heating and warm water that you can that hurricanes can start to form, or at least low systems where you have convergence occurring. And they develop most often in late summer in the northern hemisphere, where there is the most solar heating in the northern hemisphere, and where water temperatures are highest. Their initial stage is not well understood. How do they get from a tropical depression? How do tropical depressions form, and what causes tropical depressions to then turn into tropical storms and subsequently hurricanes? And when hurricane systems or typhoons or cyclones move into cooler water systems, that the cool water, which water after all is where hurricanes gain their energy, can have to be continually recharged with the heat energy that is produced by evaporation of warm water, or actually the condensation of warm air masses. As they move over cooler ocean waters or over land, hurricanes tend to diminish in intensity and tend to break up. Hurricane destruction is classified using what's called the Saffir-Simpson scale. It ranks relative intensities of hurricanes, and most folks from the eastern seaboard of the United States are familiar with these hurricane scale, the category 1, 2, 3, 4, or 5. There are very, very few category 5 storms that reach land due to the fact that thick masses of warm water are required to sustain these storms, which are rare thick layers of warm water are rare as on the continental shelves. Hurricanes cause damage a number of ways: wind damage and inland flooding from torrential rains, but one of the largest sources of damage are storm surge. That is, large masses of water that are condensed or piled up due to the intense convergence of surface winds of hurricanes tend to produce massive quantities of water that can sweep over land and cause widespread destruction. So that's the end of chapter 19. This was a quick one. We'll have one more chapter for Unit 6, And thanks for taking the time to check this out.